Okay, today's talk is going to be about quantum cryptography and quantum computing. It's an introductory talk. Everything I'm going to talk about is very minimal math. It's very minimal, just about everything but theory. And as you can imagine, quantum computing and cryptography is a sort of large subject. It's a large subject, and we're going to be moving quickly through a lot of possibly new concepts, especially if you haven't had anything to do with quantum mechanics in the past. But hopefully, if all goes well, by the time we're done, you'll have a sense of classical computing, the basic definition, and how it relates to quantum computing and how it might be different. The basic principles of quantum mechanics, basic principles of quantum computing, applications, and then practical implementations, and then I'll talk a little bit, very briefly, about where things are going. So let's get right into it. In classical computing, the first thing to know about is definition of Turing machines, which is that it reads one bit at a time. It changes the state internally based on that one bit, and then it outputs a different bit overwriting the tape. Theoretically, you could have an input tape and an output tape, and it wouldn't be any different. It's just a little more elegant to draw it this way. What's interesting, yes? Yeah, absolutely. Previous note, the slides that I'm presenting plus my notes that I'm reading from in probably a slightly better edit than what I'm looking at will be available on the dis.org website, and you'll probably find it linked off of my directory, which is my last name. So, dis.org, dis.org. Anyway, so from this machine, simple as it might seem, somebody named Church in about 1930 said that any computable function can be completed on a Turing machine, which is a pretty significant statement. Anything that you can compute can be done with these simple steps. Now, that's preparatory. You'll see where that fits in a little bit later. And then another interesting note that applies to quantum computing is Moore's law, which has said that the complexity of classical systems, of classical computers, which are the ones we're all familiar with, has been increasing exponentially. That is, the number of gates in a classical computer has increased exponentially since about 1965 and continues to do so today. One of the driving forces behind discovering quantum computing was the realization that sooner or later you're going to be dealing with single atoms. And at that point, quantum physics dominates and classical physics ends up having no meaning. And so people began looking at quantum computing as an answer initially to the problem of what would happen when we reach the limiting size of features, the quantum limit, on classical computers. Anyway, so the power of these systems, because of the technological advances, has been increasing at a rate of power 2 to the t over 1.5, which means the doubling period is every 18 months, and that's Moore's famous law. The power of the system as a function of complexity is linear, which is to say that you don't get a faster computer. Your computer is twice as fast if you have twice as many gates or twice as much memory, roughly. That is, it's not an order of magnitude faster. It doesn't go as a function of the number of gates to a higher power. It doesn't go as a function, certainly, as a power, as a number to the number of gates. It increases roughly linearly or quadratically, depending on how clever people are. And there have been improvements that have changed this rule a little bit, but basically it increases linearly. And that, you'll see, is a significant statement and a significant difference between classical computers and quantum systems. If you look at the problems that are applied to classical systems, they fall into two basic mathematical classes. There are two basic concepts in number theory. These are problems that are computable in quadratic time. So these are called P problems, polynomial time. And problems that fall into this class take twice as much time to compute, or a power of, say, 2 to the x as much time as the complexity of the problem. And a good example of that is multiplication. It generally takes about twice as long to multiply two twice larger numbers as two half smaller numbers. It's a straight function, which means that in general, although not necessarily in practice, P problems Problems that can be solved in polynomial time are what are called tractable problems. That is, problems that a classical computer can be applied to meaningfully, and you can expect to get a solution in some time. If you're doing something very complicated with a classical computer, like, I don't know, number theory or simulating some complex mechanical system, which may be defined as a tractable problem, the total number of computations might be so large that you don't want to wait for it to happen. But at least in theory, if you double the complexity of the problem, it will only take twice as long, or x to a power as long. It's a polynomial problem, and it's considered tractable. The other graph shows what happens when you have problems that are not polynomial. That is, NP problems. And NP problems may be P problems. It hasn't been proven that they're two different, there's two states. But people believe, and they've worked really hard to find an answer that NP problems are different from P problems. And NP problems are problems that take 2 to the complexity of the problem longer, or some constant to the complexity of the power longer. That is, they rise very, very quickly with the complexity of the problem. And examples of problems that are well known to be believed NP problems are factoring. And the reason why that's important is that that's the basis of cryptography. That is, it's very easy to multiply two large numbers together. It doesn't take very long. But to find the common factors of a very large number takes on the order of 2 to the x operations, where x is the size of the number. So it takes x squared, where x is the size of the number, to multiply them together, depending on what function, or maybe just x, as x is the size of the numbers. But it takes 2 to the x operations to factor them. And that's how cryptography works, or public key cryptography. The basic premise is that you can make a number that's very easy to solve in one direction, but nobody can solve it in the other direction. And very quickly the problems become what are called intractable. An intractable problem, a Turing machine can solve an intractable problem, right? We know that it can solve all problems. But when the number of time it takes to finish it, even when you take into account Moore's law and the exponential increase of the power of a computer, would be longer than the known lifetime of the universe, you would probably say that's an intractable problem. And factoring very large numbers quickly falls into that category. Factoring 1,000-digit numbers on standard computers, even taking into account Moore's law, would take longer than the known lifetime of the universe. And so that's why people today believe that if they use large keys, 1024, 2048-bit keys for their public key encryption, that they're probably going to be safe, at least for their lifetime. Now, it is possible that there's a shortcut to factoring. In fact, there's a number sieve theory that's cut the time down significantly, but it hasn't changed it from an NP problem to a P problem. It's still an NP problem. It's just a little bit better. So using these methods, 128, 129-bit numbers have been factored in reasonable 42 days using 10 to the, I think it was a teraflop of processing power, something like that. It is tractable to do for smaller keys thanks to some advances, but it's still completely intractable as you get into larger numbers. Now, what's interesting, let me just introduce this subject with a little bit of an idea, which is derived from the Turing machine concept, which is that mathematics is this derived language of the universe. That is, the language of math is universal. Not necessarily because everybody thinks about numbers in the same way, or all cultures do, but if you notice that generally, although some cultures didn't invent zeros and some did, basically all cultures have figured out addition, subtraction. In fact, those two basic things are all it takes to make a Turing machine. So there's this derived language of the universe, which is mathematics. And what's been amazing about that derived language is that quantum mechanics was derived, the theories of quantum mechanics were derived from the mathematics of the problems that were observed. They were not derived from direct observables. In fact, the observations of quantum mechanic effects that were proving the quantum mechanical theory didn't happen until later. There were some little quirks that people noticed. There was two-slit experiment, which I'll describe in a second. But the basic definition of the universe, which turns out to probably be nominally correct, that is, quantum mechanics as it stands today or will stand in the near future, was derived mathematically. And what's interesting about when you do this derivation is that you come up with some very strange results, things that don't jibe at all with our experience of everyday life. And in fact, they don't appear at all in our experience of everyday life. And here's why. One of the basic foundations of quantum mechanics is Heisenberg's uncertainty principle, which you may be passingly familiar with. But basically, it says you can't know the position and the momentum of a particle or an entity exactly at the same time. That is, you can't know it exactly at exactly the same time. You could know one and then the other with a time delay between them. You could know one or the other at the same time. But you can't exactly know both of them. And that's a very unusual statement. It's something that doesn't jibe with anything that we see in the everyday world. It's completely new concept after classical physics. And it's a profound statement because what it means is there's a fundamental limit, a quantum mechanical limit to where you can find things. But there's another thing that it means, which is something that really bugged Einstein, which is that at a basic level, it appears that the universe is stoichiometric. That is, things happen by chance or appear to happen by chance. And Einstein famously said, God doesn't play dice, and he wanted to try and find some way around it, but never did. And there are arguments that were happening between the Copenhagen School of Physics at the time, which is where quantum mechanics came out of, a bunch of guys there, and Einstein and some other people. They worked through a lot of problems and came up with a lot of seeming contradictions, things that Einstein felt, and I'll get to one of the more famous and useful ones soon, things that Einstein felt that proved that there was something lacking in quantum theory. But all of these things have found, if not necessarily comprehensible definitions, the basic concepts have been proven out in every experiment to the maximum precision that's possible. So there's a weird concept that at the most basic levels, a particle, for example, does not have a location, is intrinsic, and not have an instantaneous location of momentum is intrinsic to quantum mechanics. And from that, and from some other things, we derive the wave function, Schrodinger's equation, which is the colorful graph that I copied off of somebody else's website. Down at the bottom, those are not my colors. I assume that they describe phase transition in a moving particle, but that's not relevant to our discussion. Just enjoy the colors. So what that describes is the location of a particle. Now, what you notice is that's a decreasing function. Right? It's a bell curve, roughly, but it doesn't go to zero anywhere. You can calculate the probability of finding a particle at any distance from the classical location of that particle at any time, any distance, across the universe. Right? A particle is not in any one place. It's everywhere. It's mostly where we think we're going to find it. Mostly to the degree, the kind of numbers which are large numbers like a Google, big numbers say you're not likely to find it anywhere else other than where you think you're going to see it. But there is actually everything has a wave function. The wave function doesn't just apply to basic particles like photons. It also applies to atoms, molecules, and objects. You can compute the wave function of this. Now what you'd find is the uncertainty of the location of this is going to be something like, well, 10 to the minus 27th will be a number in it, and that gives you kind of a sense of where it's going to be. That is, it's not going to be very poorly located. It'll be located to a higher precision by, 20, 30 orders of magnitude than you could measure it. And that's just fine for any sort of classical observations. But what it does mean is that there is a finite probability that it won't be here, that it'll be somewhere else instantaneously. And I don't know how many of you are familiar with Douglas Adams' Hitchhiker's Guide to the Galaxy. Yes, good. All right, well, there was a line in that about how faster-than-light travel was achieved, and it was the infinite improbability drive, and that is actually comes from physics. It's sort of a physics joke, but the idea is that if you could, instead of trying to move things from place to place, if you could change the probability that they would be located in a different place, and you could increase the probability that it was located somewhere where that probability is now e to the minus 6,000, to e to the 1, then it would be there instantly. And now nobody knows how to do that, but it's kind of a clever idea. Yeah, definitely. Future research. So now another concept that we'll need to work with to understand quantum computation is the concept of spin and the concept of polarization. And I've taken two effects. Polarization is a direct observable. Spin is somewhat harder to observe, but if anybody's ever had an NMR, CAT scan, not a CAT scan, magnetic resonance imaging, then you've had spin has been responsible for your being able to get the cool 3D images that you get. So these are two observables, things that you can see in the real world, that have the foundation of how they work is quantum mechanical. Now, spin is a subtle concept. It's the magnetic spin of a particle. It is precession about an axis. It's not like a top, really, because it can be in any one of three axes, orthogonal axes, or at an angle between them. At any time, when you measure it, it ends up being in one of those axes. Before you measure it, it's in all three simultaneously. It's a complicated concept that doesn't have a clear classical analog, but most people like to think about it as a spinning top. And then, in fact, you can do some math on it based on assuming it's a spinning magnetic top, and they'll work out pretty well. And we'll use the concept of spin, but no, the one thing that you need to know about spin is that when we talk about spin, it's not spin like a top, like it's spinning at a certain speed, but it's spin like it can be spin up or spin down. And it can be spin up or spin down in any one of the three mutually orthogonal axes when you measure it. And when you measure it in one, it's not in any of the others. And we'll be talking about why measuring spin can be useful in a minute. But it is by taking advantage of the spin of an atom or the spin of the electrons surrounding an atom that you can do cool things like NMR, wherein the spin is a function of the magnetic field, and the magnetic field is what holds the top up. It's the equivalent of gravity. And you can change the spin of that top. You can hit it with a pulse, and if you have ever flicked a top, you know that it precesses about its axis. It's a gyroscope. It doesn't just fall over. When you knock it, it rotates like this. And that there's some analog to this in quantum computing and in NMR. And if you hit it just right at exactly its precession frequency, it will precess larger and larger until eventually it'll try to go horizontal, which it can't because it'll run into the edge of the top. But there's no such limitation on a spin of a particle. And so by putting pulses of energy into it, you can actually, when you get exactly the right energy, it's exactly harmonic, then you draw energy out of the field, the RF field that you're using to tap it, and it's actually a radio pulse energy, and the frequency of the radio pulse is the tap frequency, and you can measure that drawdown in energy, and that's what an NMR machine does, and that's how NMR-based quantum computers work. They look at the very subtle changes in the amount of energy that it takes based on the local atomic conditions to get it into precession to determine something useful about where that molecule is located, if they use a gradient field, or what that atom is attached to if they're trying to do chemical NMR where they're determining chemical structure. And all of those things will play in later. Now, another concept that's useful is polarization. And now polarization is something that people are quite familiar with. My LCD and, in fact, this LCD projector are based on polarization. And the way that they work is one would believe that has very little to do with quantum mechanics. And at a certain level, you're right. But, in fact, the grayscale that you see is a quantum effect. And the reason why it's a quantum effect is that if you take two polarizers and we orient them at 90 degrees to one another, no light passes through. That's how you create a black pixel on an LCD screen. The light is shining against it. It gets polarized in one axis. It hits a polarizer that's in exactly the opposite axis, and it stops. And so no light comes through. Pretty straightforward. Now, if you rotate the second polarizer 45 degrees, or indeed, I haven't shown this, but if you put a 45-degree rotation polarizer between the first and second polarizers, light does go through. That is, it can be polarized by the first polarizer, hit the second polarizer, and with some probability, which is a function of the angle between the two, get polarized again by another rotation. And when it hits the third polarizer, again with some function of the angle between the two, it'll go out and you'll see the light. Now, what's tricky about that, what's subtle about that, is that photons are particles. So what's happening? If you think about it as a wave, it kind of makes sense, and that's how you'd work out the equations. You'd work it out as a wave equation. But we know that this works if you shoot a single photon at a time through polarizers. You'll get 50% intensity through a 45-degree rotated polarizer, which means some photons go through and others don't. 50-50. Completely random. That's very subtle. Why does that happen? Are they slipping through? They're not. They're all being defined exactly by the same. It's not local imperfections. It's not perturbations in space-time. It's not randomness that makes them go through. 50% will go through. 50% is what's predicted when you look at it a wave, but it doesn't make a whole lot of sense when you look at it as a particle. So here's something that illustrates that wave-particle duality. And this is a concept. The wave nature of particles is pretty intrinsic to quantum mechanics. And so here, if you take two slits and you shine a light through those two slits, well, let's start with one. If you take one slit and you shine a light through it, you'll get a function that looks like if you draw a line across the peaks of this wavy function here. That's what you'd expect. You get a bright spot in the center and it fades out towards the edges. But if you put two slits, you get a complicated function because the light from each slit interferes. Now that makes sense from a wave equation. You can see that anytime if you look at a glass of water with a little wall in it and there are two breaks in the wall and you put a plane wave against that wall, the two waves will hit each other, and where the crests meet, it'll be twice as bright or twice as tall, and where the crest meets a trough, it'll cancel out and you'll get nothing. Something that seems familiar and reasonable. But what's weird is if you do this at a particle at a time, and these the black images are now, this is actually a single photon counting system. It's actually measuring single photons. And then the top image is about 10 photons, and you don't really see anything. It looks random. In the next image, there's 100, and you're starting to see an image. In the next image, there's 1,000, and you can see this diffraction pattern. This diffraction pattern is being built one photon at a time. Now, what's strange, what's very odd, is if you block one slit, you go back to the regular pattern that you get from one slit, bright in the center, fading off to the edges. If you unblock one slit, you go back to this wave function. How is it that photons going through one slit know what's going on with the other slit? Why does it make a difference? Now, it gets even more weird. Somebody postulated that if you could watch which photon it went through, if you could see which one it went through, then you would know which slit it went through, and you should get 2 lumps, one for each slit, bright in the center and fading off to the edges. You should be able to count the photons as they go through. You should be able to fool this function. So why can't you just put a little side detector at each slit and watch as the photon comes through? And then you'd know which slit it went through, and it shouldn't have any diffraction pattern. I mean, how could it do that? Well, what happens is if you watch it, any way you watch it, puts a certain amount of energy into it. You can't observe it without changing the state of the photon as it goes through the counter. When you observe it, you change it from a wave function to a particle function. Any way of observing it, any method of observing it, will disrupt it enough that it'll change from an interference pattern to a standard 2 mounds or 1 mound pattern, depending on what you've got. Now, what's even more interesting is that, as I said before, the wave function applies to everything, objects like this. And in fact, people have proven the same diffraction pattern occurs when you fire atoms through slits. That's very odd. If you think about an atom, and I mean, at photons, we always talk about photons and wavelength. We were pretty comfortable with the idea that a photon is a wave function. It's got a wavelength. That will make sense. But we're not really comfortable with the combined concept of photon and particle. But we do believe that atoms are particles. So how is it that atoms can interact? Well, it turns out that if you don't disrupt the atomic system and you fire it through, if you keep the energy of disruption low enough that you don't cross the threshold, which would be the observation threshold, that is the amount of energy that it would take to observe one photon or one atom moving through that system, then you'll form an interference pattern, just like you do with 2 slits. If you observe even the slightest bit, if you take enough energy to observe it, it goes away. You get 2 mounds of atoms past the slits. So the strange step you have to take is that, in fact, the photons in some way, or the atoms, go through both slits. Each one goes through both slits. And the reason why each one goes through both slits is that non-locality that I was talking about before, that an atom isn't in any one place at one time. It's actually spread out across space with a distribution described by Schrodinger's equation, and that spread, if it's larger than the spacing on the slits, will form an interference pattern when the probability waves pass through the slit and interfere with each other on the other side of the slit and then are detected. So everything has a wave function, and when we build quantum computers out of atoms, we'll take advantage of those wave functions, and we also have to be aware of the disturbance. And that's a problem called decoherence, which if you look into quantum computers, you'll see decoherence. Decoherence time is one of the primary measurements, and that's where it's coming from, so you'll understand that when you see it. What decoherence means is that how long does it take to go from a wave function, a wave-defined system, to a particle-defined system? That's a decoherence time, and it's a function of the interference of all the environmental factors. And so if there's noise in the room, or there are vibrations, or there's electromagnetic energy penetrating the apparatus, and that energy passes a threshold, then you'll lose your wave function and you'll be particles. And you'll be in a fixed state. It won't be interacting as a wave anymore. And that's what you do at readout. Although all computations in quantum computers are performed when the particles that build the quantum computer are defined by their wave functions. And that is, they're not behaving like particles, they're behaving like probability waves. So now here's an even stranger experiment, which I'll just run through really quickly, but this one is extremely counterintuitive. If you generate exactly equal path lengths, and you shine a light through a half-silvered mirror, split it, bounce it off 2 full-silvered mirrors, and then recombine it in a half-silvered mirror, you would expect each detector to see 50% of the photons. But if the path lengths are exact, in fact, only the top detector will see any photons. And it's the same problem, because what it says is that each photon is actually traveling down both paths, no matter how long those paths are. You can make those paths fill the room. It's not a localization problem. There's something very counterintuitive happening there. You have a photon traveling both paths, large distances, and recombining and still having interference effects. If you block one of the paths, which is the lower slide, you get 50% split, which is what you'd expect. Well, 25-25 because you've lost half the beam. But you split the remaining beam 50-50, just like you'd expect. The 2 paths no longer interfere and it splits. If you remove the block, the two paths interfere once again, and not shown if you put a sliver of glass in one of the paths, which slows down the progress of light. That is, light moves as a function of the index of refraction of the material which it's moving through, and glass has a different index of refraction than air, and so that means that light moves a little slower, and this is like a time delay line for light, and light slows down on one of the paths, and if you get the right thickness of glass, you can switch which detector sees the photons, and you can pull the glass in and out, and you can switch photons coming from one detector to the other, just by changing the index of refraction along one path, or slightly changing the path length would do the same thing. So here's one of the more unusual concepts and all of this leads to a very odd concept. And this is one that really bugged Einstein. And this was called spooky action at a distance. And here we're going to combine the idea that wave functions can be tangled together, which is what we were seeing in that two-path experiment, and that atoms have spin, which is what we're going to look at here. And so in this experiment, what you do is you take a small particle, and this actually has practical applications we'll get to in a minute, but you take a particle that's going to decay, and that particle, you choose it to have net zero spin. And by conservation of momentum, that is, you can't have more momentum at the end of the experiment than you started with at the beginning, considering losses. Same thing with energy. Physics is all conserved. That particle decays into two particles going in opposite directions, two photons, for example. They will each have spin half. That's the unit of spin. One will be up and one will be down, so the two spins cancel. They have to cancel because you started out with zero. Now, what's interesting is that the spins have to be in exactly opposite directions, no matter what the basis angle is. If the basis angle is in z, the other one has to be down z. If the basis angle is in x, the other one has to be in negative x. Y, negative y. They have to be the opposite, because otherwise angular momentum wouldn't be conserved. But before you measure it, the basis state is indeterminate. There's nothing that says it's going to be up, down, left, or right. And you can actually detect when it's an indeterminate basis state because it'll have interference effects. So if you run these two particles through an interference system and you measure the interference of the two basis states, you'll actually measure the quantum interference between them, and you'll see that they interfere as if they were still defined by wave functions. But if you measure it before so you know what state it is, then you can kill those interference effects, just like the guy looking at the two-slit experiment does. And the interference effects go away. So you can prove that there's an interference effect. But if you know that the particle going to the right is up, you know that the particle going to the left is down. So if you measure the right one, is the left one going to interfere? It doesn't. It can't. Because you know which direction it's pointing. You know because you know the direction of the one on the right. Now this gets very strange. This is very counterintuitive, and this really bugged Einstein. He thought that this implied that there was a failure in quantum mechanics, in fact, and I assume until his death, that there was an intrinsic failure, that there had to be local information that wasn't described by quantum mechanics, because how can you decay a particle in the center of this room, measure its spin at that end, and change its spin at that end instantly? This implies there's information being transmitted instantly, faster than the speed of light, across the room that defines that particle on the basis of that particle. Well, it's not as strange as, it's strange as it sounds. There is a mathematical reason why that's true, which is that these are mathematically derived functions, that they have a wave function that starts to expand when the particle decays, and by the time it's done, it's all the way across the room, and information you gain about that wave function applies to both particles simultaneously. Now, this is actually useful for sending keys. You generate particles in the middle and send them down both directions. I won't actually describe how that one works. I'll describe how it works with polarization, which is similar. It's the same basic principle, but this one's a little bit more complicated because of the number of steps it takes to measure it. But you can imagine that if you measure something, you're actually sending information to the other side by that measurement, and you can use that translation of information usefully. That's a very recent development in the last 10 years. So from those building blocks, I'm going to try to describe the basics of what a quantum computer is. And there's a couple of elements. There's a large field of this, but I've chosen a very small subset of some of the things that build a quantum computer. There's an infinite number of gates in a quantum computer. I'll just describe one. Bits have an analog. They're called qubits, quantum bits. And when quantum bits are organized, they're organized in a register, and what's key about that register is that it's entangled, that the bits in that share quantum information just like those two photons traveling in opposite directions, and that has a very useful property. So in 1982, Feynman proposed a quantum computer, and Feynman proposed this as he was talking about the limitations of a classical computer. And one of the things that you try to do with classical computers that's extremely hard is modeling the quantum mechanical behavior of multi-particle systems. So we can describe that wave function and generate a graph for one entity as it expands, but remember that entity affects everything in the universe, right? Not just mostly locally, but everything in the universe is affected by the wave function of that one particle. And so if we want to describe realistically any quantum system, you have to take the simultaneous solution of all the quantum equations, and that is an NP problem. That is, the complexity of it increases exponentially with the number of particles in it, and it very soon becomes intractable with classical computers. And Feynman was frustrated with this, that he couldn't simulate quantum systems on classical computers, and he proposed that you could build a quantum computer that would intrinsically solve these quantum problems. And a guy named Deutsch, I don't know, I'm sorry, I don't quite know how to pronounce his name, but we'll just call him Deutsch, in 1985 showed through the same basic process as Turing's machine, as Church's thesis on Turing's machine, that you could in fact use a quantum computer to solve any general problem based on analogs to binary bits and gates. Now, in practice, you wouldn't make a quantum word processor. It just doesn't make any sense. But you would make a quantum code breaker. And we'll see that quantum computers a little later apply most powerfully to a special class of problems that is currently a very small subset of NP problems. But remember, this whole field is about 5 to 7 years old, so there's not too many equations yet that have been worked out, too many algorithms that have been worked out for quantum. But the ones that have been worked out are surprisingly powerful. So what is a quantum computer? A quantum computer is, in this very simple illustration, what we're saying is that you can affect a change on an atom. That is, in this case, and I will be using this illustration through it, what you have, one of the things that you can look at that's a quantum state is the excitation level of a single electron circling a hydrogen atom. And quantum mechanics tells you that it can be in several allowed states, that is, energy shells, which you might remember from high school chemistry or something, and that those allowed states, if it's in a higher state, it's excited. When it comes back down into the lower state, which it'll decay to with a characteristic time, it'll release a certain quanta of energy, and that it usually is light, and that's how fluorescence works. In fact, that's how light bulbs work. You excite with heat, you excite the electrical shells into an excited state, and they collapse, and when they collapse, they release a photon. When you do that in a well-controlled way, like with a gas lamp, they collapse to very specific states when it's not thermal motion, that is, when it's electrical excitation or something else that's a controlled energy. They collapse and they release photons that are always the same energy, and that's how you get nice colors out of neon bulbs. We can use it for a quantum computer because what we can do is apply a pulse to an atom and bring it up into its excited state or bring it down into its lower state, and we can call those two states 0 and 1. And we can apply a half pulse, and the half pulse will leave it in an indeterminate state. If you measure them, you'll find that if you apply half a pulse, half go into the excited state and half go into lower state. But if you don't measure it, they're in that indeterminate state. The superposition of two states is what they call it. That is a superposition of the excited state and the unexcited state simultaneously. It exists in both states simultaneously. And that's, for example, what happens when a photon hits a beam splitter. It exists in a superposition of both states of having gone through the upper path and the lower path simultaneously. And the math of that superposition is what gives you the interference effect. It's a wave function, and there's an interference effect. So I just basically ran through this one ahead of time. But so a qubit is a particle in a superposition of two states, 1 and 0. Each entangled state pair represents a dimension for the system of qubits. Now that's an interesting statement, and it comes from a fairly complicated explanation to why that is true with a word called Hilbert space, and I won't get into it. But basically, in a quantum computer, each qubit represents a dimension of the system. So a 4-qubit computer is a 4-dimensional processor. An 8-qubit computer is an 8-dimensional processor. Each of the excited states is orthogonal. Orthogonal in a mathematical sense, not in a physical sense. But in a mathematical sense, you end up with an 8 or n-dimensional computer where n is the number of qubits. And if you look, I put this little Dirac notation, which is the thing on the bottom. And if you read up, the reason why I wrote it down, if you read up on this, you'll see the Dirac notation all over everybody's explanation of what quantum mechanics is. And what that little notation means is a superposition of states 0 and 1. The particle is in both 0 and 1, and that the math follows from Dirac notation. So if we wanted to build an entangled register, say 3 qubits, in 3 entangled states, that register would encode simultaneously for all 8 possible values. This is a significant difference from a classical computer, which would encode simultaneously for 1 of 8 possible values. In a quantum computer, When all the states are in superposition, that is typically when they're being gates are being applied, when functions are being applied to them, it's a superposition of all 8 states. So what that means is that the power of a quantum computer increases as 2 to the n, a binary quantum computer. You could actually make quantum computers with multiple states, but binary is easier. Binary power computer increases as 2 to the n, where n is the number of qubits. That is, the power of a quantum computer increases exponentially with the number of elements in it, not linearly. And that has some intuitive sense of why you could use the exponential increase in power in a quantum computer to solve, in polynomial time, exponentially difficult problems like factorization. And in fact, that's true. So here's a basic gate. This is the universal gate. And basically what it does is it takes a 0 state where the first bit in the quantum gate is the control bit, and the second bit is the ACK bit. And so if you have state 0, it goes 0 to 0, 1 to 1. So this is one of the more basic things. So if we look at the atoms, if you have an atom in, let me pull up my page. I'll read this one out for you because it is actually a little bit complicated. So suppose you have the green atom, right, in an indeterminate state. That is a superposition, and the blue atom is adjusted into a known state. And you can adjust the blue atom into a known state by applying a full pulse to it. Set it high or set it low. Say it's in the ground state, which is what's shown here. The blue is in the ground, inner electron. The green is in the superposition. I'm illustrating it by having 2 atoms superposed on top of each other. I don't think you'll see that too often in the literature. It's probably not exact, but anyway. A pulse of energy halfway between the 2 states will put both into an intermediate state, the combination of which depends on the energy, the initial energy of the green atom. That is, that the superposition of 2 states, after it's been hit with a pulse of energy not high enough to bring both into the high state or bring both into the low state, will put them both into a superposition, but the total energy of that system will depend on whether the blue atom was in the low state or the high state. So that's a useful property. Now we have a system that initially we have 1 known and 1 unknown. We apply a pulse of energy, we have 2 unknowns, but the exact condition of those 2 unknowns is dependent on the control bit. If we apply another pulse of energy, and if we knew what the control bit was, we could know exactly what pulse of energy to apply. We'll resolve both bits, the indeterminate bit and the known bit, back into their known states. The output of the indeterminate bit will then be a function of whether the control bit was in the high state or the low state. Okay, close enough? In the last step where we do readout, we're doing the observation step, which collapses the wave function. So we actually measure them. The wave function's collapsed, and they both are resolved into a known state. They have to be known. And that's the simple gate, and it turns out that you can build, not necessarily efficiently, but you can build all necessary gates from the C0 gate if you apply them correctly. There's a universal binary gate as well. You wouldn't build a computer that way, but you could if you were trying to brute force it or just to prove that you could. So those are the basic building blocks of quantum mechanics. Those are the basic building blocks of quantum computation. And what I'm going to talk about now is some of the applications of it. And I apologize, there is a little bit of math in this. I've tried to minimize it and go through the steps as quickly as I can. But there has to be a bit so that you can understand how it works. So one of the most obvious problems is factorization. A guy named Shor came up with, not too long ago, oh yeah, I guess there is a bit of math there, huh? He came up with a method of using a quantum computer to find factors in polynomial time. And as you can imagine, this is a very sort of persuasive argument for building quantum computers, because the implication of it is that if you could build a quantum computer of sufficient size and power, you can solve factorization in polynomial time, which means that encryption is based on factorization is no longer secure. And in fact, one of the consequences of this is that the security of all current cryptographic systems rests on the technologic advance of quantum computers. That it is no longer like the end of the universe kind of time. Is it possible, and it's not known that it is, but is it possible to build a quantum computer of some 5,000 qubits, which is what it would take to practically implement this algorithm with error correction and everything else involved? Is it possible to build that computer? And when that computer is built, codes fall in like about a second. That's about how long it takes to break a 1,000-bit number. So it's a pretty powerful concept, and that's why I'll take a little bit of time to go through it. So one of the steps is that this first little equation is probably going to end up not being too useful. But anyway, in factorization, what you do is if you take a function of x that is an x mod n when you're doing factorization, when you do any function of the number that you're trying to factor in a modulo arithmetic, which means you divide by n, which is the mod n, and then you take the remainder. And so you take any number and you apply this x, a to the x, where x is the number, mod n, you'll end up with periodicity, and that periodicity is useful in computing the factors. So there's a trick to finding factors, and it's used in number sieve theory that's a faster method of finding factors. But typically on a classical computer, finding that period, which is called r for whatever reason, finding that period takes about as long as brute forcing it. It's a little bit of a speed up, but it's not that much of a speed up. It definitely doesn't take it from an NP problem to a P problem. You're still talking about something that takes exponential time. But what happens is periodicity is something that you can exploit in quantum mechanics in parallel. So let's see if I can describe this in a really easy way. To solve this function on a 2-qubit system, that is, you have 4-qubit registers, an input register where you've set the values of the input register to be the superposed states of the numbers to be factored. And the output register in this case has been, we know what it is, it hasn't been read yet. And then we apply that function fn of x, which is a to the x mod n, to that system using a complicated system of gates. So let's just assume that we've built that set of gates, and we can now apply this function from that set of gates. We can encode that function into a set of gates and apply it on these registers. And after we've applied the function on the registers, we'll end up with, in the first register and the second register, a superposed entangled state between both registers, all the registers working together. Now we have n to the 2, or x to the 2n power working on this problem, where n was the number of bits of the system, which will be a sum of all of the states. There's only 2 states, but rather than write them out, you'll see it as a sum. So the 2 states now, the state on the right register depends on the state of the left register as this function that we've applied. So then we do a readout of the second set, and what we get from a readout is that function. I'm not sure that's going to make sense, but we get that function, but we've left the first state in a periodic set. We don't really care about the function output, but by reading it out, we've left the first state where the power, the relative amplitude of the 2 possible superposed values of each bit, as you go down it, is more likely to be periodic in R than not. And remember, finding R was the hard problem. So by doing this function of x on it on the 2 qubits, then doing the readout, we get back to the first 2 qubits, are now have more probabilistically encoded in them that value of R. And so if we do a quantum Fourier transform, which will read out that value, we get R. That's only 4 steps. So we build a register now as big as the number, and this is why you have to build a big one, as big as the number that you want to factor. You put the number you want to factor into it in a superposed. You apply a unitary transformation, which puts it into a superposed state. Not really too important. Apply these 4 steps, and the input register, after the application of the 4 steps, now gives us the period that we were looking at before. And from that period, we find the greatest common divisor of the number n that we were looking for, and a plus or minus r over 2 plus or minus that the second line there. We apply that function. We do that classically, and we get an answer almost instantly. That's how a quantum computer can break factorization. And what's happening is, the reason why it works is that the gates, that function, is applied to all of the bits in the register simultaneously. That's where the power comes from. In a classical computer, you apply functions to bits one at a time or in groups. In a quantum computer, you apply the functions to all of the bits simultaneously. So we get a function. That was the one I was going to go into in the most detail. I'm sorry if I lost some of you, but that will be the most math that you'll see in this whole thing. And if it was frightening, I'm sorry. I think I didn't quite pass Feynman's test of, if you really understand something, you can explain it so everybody else can. And I'm sorry if I didn't quite get there, but I'll work on it for next time. So another function that you can do that somebody else, this guy named Grover, figured out is that you can do a search function, this is a little bit simpler conceptually, although the number of steps is actually larger. But the basic idea is that if you're searching for something among a list, and for example, you say you have a phone book and you know the phone number and you want to find whose name that associates with, you have to search through the phone number. And there's no fast way to do this. It's on average going to take n over 2 tries, where n is the total number of entries in the phone book. That is, it'll take quite a while. If you use a quantum computer and you apply the search function, the search parameter, to all of the bits in the register, all of the entries in the register simultaneously, it will take on average root n over 2. So that's pretty good. If there were 16 items, it takes on average 16 over 2, or 8 steps to do it classically. If you do it quantum mechanically, it takes an average of 4 over 2. 2 steps to find the search. That's much faster. Now, the application of this is interesting because if you're trying to do DES encryption, if you have a DES problem, basically what you want to do is algorithmically test all possible keys. There's not a factorization shortcut to it. You're going to algorithmically test all possible keys. And that takes a rather long time. The number of keys is huge. It's not necessarily an intractable problem in the sense of factorization being an intractable problem, but it's certainly a hard problem. Whereas in a quantum computer, it suddenly becomes a relatively easy problem. And in fact, symmetric key encryption falls to this algorithm. And let's see, the little bit on the bottom is if you try to use a classical brute force attack on I think it's a 56-bit key space, it would take 1,000 years testing 1 million keys a second. And there are computers that can do this. There are computers that can do quite a bit more than that now, classical computers. But, excuse me, at the same basic clock speed on a quantum computer, you would do it in 4 minutes. That's a pretty significant speed up, and it really changes the relationship of security and encryption. Now, here's what I was going to talk about a little bit with quantum key distribution. Quantum key distribution is an application that's actually the most advanced in quantum cryptography and quantum computers. It's not actually a computational function, so it's more of a quantum cryptographic function. And suppose you have the problem of you're trying to distribute a key. Let's say, for example, we have quantum computers, and now we know that our public key is useless and our private key encryption is useless. In fact, the only provably secure method of encryption is a one-time pad. So all of a sudden now we're faced with the problem of having to use an old-fashioned one-time pad to encrypt our communication, and that means we have to send keys all over the place. We have to generate random keys, and we have to share the keys. And how are we going to get the keys from one person to another without having them intercepted? Well, it's actually a very difficult problem, but fortunately quantum mechanics has an answer for that. And that answer is the whole basis of that splitting atom is one case of it. And that measuring one state collapses the wave function, and you can detect the collapsed wave function. So although this isn't a provably secure method of transmitting the keys, that is, it's possible for someone to eavesdrop on it, it is impossible to eavesdrop on it without affecting the data in a way that can be detected. So let's describe this. Let's say Alice prepares a pulse of light, typically one photon. You don't want to use multiple photons, but a single photon that goes through a polarizer and gets put into vertical polarization state. And let's say Bob measures it with horizontal polarization. Bob's measurement will show no photon, that is a 0. If he measures it in the vertical polarization direction, he'll get a 1. Now, there's 2 orthogonal basis states that you can measure with mechanical polarizers. That is 0, 90, there's an infinite number, but useful ones, 0, 90, 45, 135. So if Alice says ahead of time she's going to encode her bits in either 0, 90 or 45, 135, and Bob will then measure randomly in either 0, 90 or 45, 135, when he chooses the same basis state, he'll get a 0 or a 1 just as Alice prepared it. If he chooses in the 45, 135, he'll get either a 0 or a 1, but 50-50. That is, his answer will be half right. So if Alice and Bob later compare which states they used to prepare and measure, which they can do publicly, but don't compare the results, and they say, and that's what we start with on this table, if Alice sends with vertical plus is vertical horizontal polarization, x is 45 135 polarization. So she's preparing bits and she's sending them off plus x plus plus x x plus. And what Alice ends up sending to Bob is a vertically polarized, a right 45, a vertically a horizontal. So there's a string of bits that she's sending. And Bob then he measures, and he's choosing a different random measurement basis. They don't compare their measurement basis. Each of their measurement bases is random. Half the time, on average, he'll get the measurement basis the same. And so now Bob and Alice share which basis they measured in, and where they agreed randomly, they know that they have correct bits. They have the same 2 bits. And everyone else they throw away, and they get a key. Now, if Eve tries to intercept and she measures, she could detect the photon and then regenerate the photon in the same basis state and send it along to Bob. And Bob wouldn't know. But she has to choose a basis state to measure it in. And half the time she's going to choose wrong. And once she chooses wrong, for those half that she chooses wrong, Bob's going to measure it. And once she's done her measurement, she's forced it into the wrong basis state. And when Bob and Alice happen to agree on a bit that Eve has measured wrong, they'll get 50% of the time the wrong bit. They'll see their error rate suddenly go up. And that means that the key distribution is corrupted, and you throw it away and you start over, or you hunt down Eve and begin again. So that's how you can distribute now a one-time pad in a provably secure method. So now there's a couple of practical implementations that have existed. This is how quantum computers are being built right now. One of them is an ion trap. And so that's it with all the math and functions. This is just a description of what's out there. You'll see ion trap research, and in an ion trap you hold atoms that are in excited or unexcited states, that is state 0, state 1, in a carefully controlled magnetic field, and you can apply laser pulses to raise them from state 0 to state 1, and the application of those pulses is how you generate your gates. Another way that Gershenfeld is doing at MIT is using NMR-based systems. And one of the things that we talked about very briefly was the rate at which decoherence happens, the effect of the outside world. There's 2 ways to beat it. One is to isolate the system completely. That's what you do in an ion trap. The other is to use redundancy, which is what you do in an NMR system, where their quantum computer is actually a long hydrocarbon molecule. Each hydrogen-carbon pair is a qubit, and they can share interaction, and they share interaction down the length of the chain, and that you can apply magnetic pulses to them to change the excitation states, and that's a quantum computer. Neither of these look like they're going to scale to very large computers. There's one more experimental one that's going along right now. That has the possibility of being much bigger. It's high Q optical cavities, and each of your qubits is isolated in an optical cavity, and they're connected by fiber optics. That actually, nobody's built one yet, but you might be able to miniaturize those and use basic microfabrication techniques to build complex quantum computers with them. But it's yet to be proven whether that'll actually work. So in conclusion, what's interesting about quantum computers relative to classical computers is this power function of quantum computers. That is, that the power of classical computers increases linearly with the complexity of the computers, and the complexity of the computers has been increasing exponentially. So since 1965, the power of classical computers has increased exponentially, and in this graph, classical computers are the little triangular pentagon little things on the top graph. It's starting at the top. And I'm assuming that year 0 is 1995, the first qubit, single qubit experiment. In 1995, there was 1 qubit, and there were classical computers were about 24 million times faster than they were in 1965 when Moore proposed his law. They have been proceeding exactly according to it. If you go out 19 years, the graph looks pretty flat here. 19 years, classical computers increase to something like, E16 times their current power, which sounds like a lot of fun if they could keep proceeding that. But quantum computers now have had, over the last couple of years, a doubling rate. It's not 1.5 years or 18 months, but every 2 years, roughly, we've gotten another doubling of the number of qubits that we can build. From 1 to 2 to 5, there's an 8-qubit computer working now. If that proceeds apace through the same period, in 19 years, quantum computers will be E224 times faster than they are right now, which is about E18 times faster than the fastest classical computers. In fact, if you take that out to 1936 years that it took classical computers to go from single gates to where they are now. If you take it out following 1996, quantum computers should increase to E 102,605. That is 10 to the 102,605 power, times more powerful than they are, assuming everything continues apace. That seems utterly ridiculous. That's 10 with 102,000 zeros after it, times faster than they are now. That's a really big number. In fact, it's one of those very large numbers because the estimated total number of particles in the universe is only E97. So how can it be that it would be that much powerful? But what's interesting is that it may seem ridiculous to consider that kind of power, but the universe has E97 mutually interacting particles in it. And we can't do a multi-particle quantum simulation with more than like a dozen particles in any sort of practical amount of time, in any time in the near perceivable future with a classical computer. But a quantum computer, the universe, is solving that problem for E97 particles at a rate of 1 second per second. Think about the power of a classical computer it would take to do that. It's actually not inconceivable. So that's it. That's the concluding remarks.